Hi, in this video, we're going to take a look at model complexity and generalization in supervised learning. Okay, so the big idea here of what we're really driving at is that when I fit a model, it may look really good on the data that I built the model on, that I trained it on, but when I go and actually put the model in production, when I actually use it, I might get some problems. I might have horrible inaccuracies. And what we want to look at is kind of like balancing some features when we're working on our supervised learning model. All right, so what we want to do, we want to get the model that is as accurate as possible with as little complexity as possible. The more complex my model is, the more prone to overfitting I am. All right, now overfitting, that is where we are detecting features in our training data that's not in our target population data. This will always happen. Take it as an axiom that all models overfit on their training data because there's always a difference between the data you're working with and the data you're trying to make predictions on. There's always a difference. And so doesn't matter what your model structure is, you're going to overfit. But it's kind of like a gray scale. And when I look at that gray scale, I want to see, hey, it looks like, I'm not overfitting unreasonably so. We want to, check things. We're going to check our training statistic, validation statistic, and our test statistic. And we're going to compare training to the other two to see, hey, if there's a large gap in it, that's an indication that I've got severe overfitting. And that's how we're going to detect this. Now, the more complicated models can pick up features in your data that less complicated models can pick up on. And so what I'm going to be trying to do as I build a model, I want to basically capture as much information as possible in my training data for the actual target population I want to make predictions on. But I can overshoot the mark. I can, pick up too much nuance in that training data, which leads to overfitting. All right, so our goal is to build a model or models that execute well on unseen data. So the data that I haven't seen, the data that I need to make predictions on that's coming down the pipe, but I don't have it yet. And so what we're going to do, we're going to actually hold out some data that's going to be our validation data, our test data. We're going to hold this back in my training process and not include that. And this is going to take the role of the unseen data. Now, on my validation data, my test data, I actually know the outcome. I know what the true target variable values are, and I'm going to use that as a proxy to try and anticipate how the model actually perform in the future on real unseen data. Now, the level of complexity that we introduce in our models will dictate how well these models will generalize to fresh data points. If I have a very, very complicated model, I can pick up nuance in that training data that I would not have picked up on in a simpler model. Now, all models overfit on their training data. Our aim is to train to get the best model possible. And a good rule of thumb is that the more data I have, more rows of data I have in my data frame, the more complicated of a model I can have. If I have very little data, I need to have a very simple model to work with. Right now, we have something called overfitting and underfitting, and we need to like balance this. And this is not a binary problem. This is kind of like a gray scale on there. And so it's along a spectrum. And we want to use our training data, our sample data, to detect patterns in the population that we're going to be actually making predictions on. There will always be a difference between our training data and the population that we want to model. And so we always have to be mindful of this difference as we work through. All right, so let's go ahead and load some data to work with. We're going to be doing just a regular old vanilla multiple linear regression model, just so that we can get a feel for what's going on. When you're doing a regression task, I strongly recommend that you always build a multiple linear regression model and a tree model because these are simple, these are easy to understand, and they have pretty solid interpretations. If I'm doing a classification problem, I'll do the same thing with logistic regression and tree model also. Just use the most fundamental models that are easy to interpret, easy to understand, easy to get inference out of, and that will help guide me through the rest of my project. Even if I'm going to do, a neural net or k nearest neighbor or random forest stochastic gradient boosting, any of those, I still personally use a vanilla regression model in my process. All right, so in my data set, I've got sale price as my target, and this was transformed using Yo-Johnson to get the distribution to look more normal. Numeric variables were imputed using the median, and they were also transformed using Yo-Johnson, which is similar to Box-Cox, but Yo-Johnson it will allow negative values and zeros. And then we centered and scaled to have mean 0, standard deviation 1. This is for regression. This will not actually improve the accuracy of your model, but this will improve the performance on other models, such as support vector machines, k-nearest neighbors. We want to have, especially that rescaling the standard deviation. Now, categorical, we imputed with an NA. We created an NA missing level in there, and then I binned the categorical predictor variables into 3 levels of low, moderate, and high. And so ones who had lower sales price were in the low, those with higher sales price were in the high, and in the middle was moderate. And I tried to set the cutoffs so that we had that we had approximately equal counts for low, moderate, and high. Now, I use the conditional average of the predictor with the sales price, taking the average to decide which levels were low, which levels were moderate, which levels were high. Now, something about this, with this Yo-Johnson on the sales price, after I make my predictions, I'll actually need to perform an inverse transform, which I fitted previously in another video, to be able to convert back to the actual sales price. So here in the models I'm building, I'm going to be predicting the Yo-Johnson version of sales price, not the actual sales price. And now when I load my data, you'll notice I have a very large, not large, but a decent size dictionary for the data types. This can greatly speed up the loading of your data time. And I'm also using PyArrow to load my data from a CSV. This, in my experience, will greatly improve the time that it's faster. And so you'll notice that I've got ID, and then everything else is a float. And why is it a float? Because all of the categorical data has been converted over to dummy variables already. All right, let's talk about model complexity. All right, there are 3 sources of model complexity in my eyes. First one is the mathematical structure of our model. Next one is the number of predictor variables. And next one is the number of parameters. All right, so the more complicated the model structure, the more prone to overfitting I am. The more predictor variables I have, the more prone to overfitting I am. And the more parameters I have, the more prone to overfitting I am. So we want to what we want to do, we want to use these as far as we can go to improve the situation without overshooting it. I want to take, depending on my data, depending on the problem that I'm working on, I want, to take a mathematical structure that will pick up nuances in the data that other simpler structures might not pick up. And I want to use as many predictor variables as it takes to get a good solid model, but I don't want to have too many in there. When it comes to your predictor variables, and also to some extent the parameters, you can think of it as if I'm cooking, just throwing in more ingredients is not going to improve the soup. I only want to put ingredients that complement my goal and what I already have in that soup. And so we don't want to throw in everything. We just want to throw in the good stuff. And so keep that in mind. So our mathematical structure, the complexity of the mathematics of the model, can identify nuanced patterns that, but it can also pick up the noise in my training data leading to overfitting. And so I want to strike that right balance. More predictor variables can increase the model's complexity also. With greater complexity, the model has increased flexibility, but also has more of an opportunity to overfit. The more predictor variables you have, the more prone to overfitting you are. And also, the more parameters a model has, the more dials and knobs there are to adjust and fine tune, which again can lead to overfitting. So everything that I do, if I increase the number of parameters in some way, I increase the number of predictors, again, more complicated model, I can pick up more nuance in my data, but I can overshoot that mark. And it's going to be better to underfit than overfit. Now, model generalization, this is the idea of how well the model that I just trained with my sample data will actually perform on unseen data. If it generalizes well, it likely capture the underlying patterns in the data without picking up the noise that is the difference between my training data and my population. However, if it generalizes poorly, it's likely to overfit. Yeah, no, I'm gonna delete that right now. There is an error on there, and likely do a little bit of on video correction to underfit. Right now, you have to overfit. There we go. All right, boom. So if it generalizes poorly, it's going to more than likely overfit. Now, overfitting and underfitting. Overfitting occurs when the model, picks up features and aspects of the training data that's not in the target population data. So this includes things like outliers and noise aspects in the data. And so it's possible that I could have near perfect mean squared error, near perfect mean absolute error on my training data, but then have complete junk on my training and validation data. And so that's a sign I have overfitting. When I have when my training statistic is like really, really good and my test or validation is really, really bad, that's a severe sign of overfitting. That's my number one way of checking. Now, underfitting is when we don't pick up the full potential of our data. Now, this isn't good either. We don't want to overfit, we don't want to underfit, but if I underfit, what usually happens is that how the model performed, like when I'm building my model, is usually how it will perform when I actually put it into production. And because of that, it's better to underfit than overfit. When we underfit, we know what's going to happen in the future with this model. We know about how accurate it's going to be. It's not going to be perfectly accurate ever, no matter what I do in any reasonable situation. We won't have a perfect model, but I at least know like how it's going to perform. When I overfit, though, what ends up happening is I think I'm like, yeah, this is going to be great. I got a good model. I'm real excited. I expect gold, but I get manure. If I wasn't, doing this professionally, for teaching, I would use a different word than manure. This can be a serious problem. I have been in this position with predicting biology results when I was at the school district. I had, like 50 models I had to build, and my biology one, high school biology, was crap. And I ended up having to just own it when I was in that position. You don't want to be in that position. If I would have been less aggressive about working on the accuracy, I wouldn't have burned myself. And remember that overfitting and underfitting are not binary. They're like a continuum. And we're trying to strike that right balance. All right, so let's go ahead and let's do something very, very stupid. I want to do something that you should not do so that you can see like what will happen if you make this mistake. My goal is that I'm going to walk up, I'm going to fit a model that's extremely overfit, and I'm going to get myself smacked in the face by a poor quality model. And then you can see what this is like. And so hopefully when you're building a model, you'll see, hey, whoa, I'm getting bad vibes from this. I need to back off and reevaluate the situation. All right, so what we're going to do is I'm going to do a one predictor variable model. I'm going to use polynomial regression, and I'm going to, so one predictor, one target, but I'm going to have a lot of parameters using powers of the predictor variable to overfit my model. All right, so let's go ahead and do this. So what I'm going to do is every time I have a non-duplicated value of my target variable, I'm going to put that in my training data. And so I'm going to have very, very, very few actual observations on here. And I'm going to go through and I'm going to fit a model. All right, so you can see that I've got, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 rows of data in my training data. I'm going to overfit. I'm going to overfit bad. And we're going to see what happens. All right, so I have 9 observations to fit a model. Now I'm going to go through, I'm going to fit a polynomial regression of degree 100. I didn't even know Python would even execute this. I was messing around. I was going for like 9 and stuff like that, you know, just to see what's going on. And I'm going to go and I'm going to fit this model and let's see what happens. So here I'm doing something extraordinarily stupid. A good rule of thumb is, in general, you want to have 30 times. So if I take the number of parameters, multiply by 30, that is the like the minimum amount of data I need for this model. That's a good rule of thumb. If I have millions and millions of rows of data, this usually isn't a problem. The more data I have, the more complicated my model can safely be. Here I've got 9 rows. All right, so really, if I'm going to be doing a model, I should be doing simple linear regression or maybe a very, very, very short decision tree. That's all I should be doing with this data. Now, 9 observations, that can happen in real life. It might be that data is really hard to get. It might be that data is really, it could take a long time to get. It might be that it's expensive. It might be that it just took a lot of work to get a little bit. Or it may be that you ended up filtering out a bunch of junk data. This is when you get into this position, it's really disheartening when you have a ton of data and you find that, well, you know what, the stuff that's actually worthy of using is a very short list. I've seen researchers almost cry over that. Like they probably like left the room. They did leave the room, and they may have like had tears, but they looked like they were gonna cry when they left. And when I hated being the bearer of bad news. So here I'm gonna. So what we're doing here is that I'm doing the transformation to get the predictor variables off of this. And so what's effectively happening is that we're doing an exponent of that one column, and we're doing exponent over and over and over of it to get a new training data matrix effectively. All right, so here I am fitting everything on that. And now I'm actually going to do the transformation on it. And then I'm going to go through and actually do the regression on it. So you'll notice that here I'm transforming the data. And so here, this is the object that transforms my data into the polynomial columns. And then I'm going to transform the data I actually want to fit on. And then I'm going to actually fit the linear regression model off of this. So I'm doing polynomial linear regression. And you can see I've got a ton of predictor variables. Now you'll notice that these are all very, very small. These are all very close to 0, at least as far to my eyes. And so what has happened is that scikit-learn knew not to let me do this. Scikit-learn stopped me from doing something stupid. And so it actually is protecting me from this. If this was a real life project, I would I'd be very grateful. For the purpose of this video, I'm trying to show you something stupid, so I'm kind of frustrated with this. I actually wanted scikit-learn to go in and go off the rails, but decided not to. So yeah, what are you gonna do? All right, so now let's go ahead and figure out what is going to be the predicted value where I go from -3 to 2.7. That's the range of my my predictor variable data. And so you can see that, so yeah, we have, see, -3 up to 2.62. So, going inside that range. So I'm interpolating, not extrapolating. And what I want to do, I want to get all the possible values in that range, practically speaking. And so that way I'll be able to plot the line of what the predicted value looks like for each possible predictor variable value. And we're going to go in and form a line on top of the scatter plot. So let's go ahead and just show you what that looks like. And so, you'll notice I've got, e to the 10. So in scientific notation, that is an exponent of 9. That does not, like here, realize that I didn't have anything nearly that big in magnitude at all in my actual value. So you can see that there is something bad going on. I've got values that are just well and truly unreasonable. And it's not just one, it's a whole series of them. All right, so let's go ahead and do a scatter plot. So here is the predictor variable value. Here is the sales price, the target variable value. And we can see that there's kind of what looks like a linear trend. Now, it may be a little bit more nuanced than a straight line. Because of overplotting, I can't visually see that. But I'm expecting to see something that looks like a straight line that goes about like this. Something like that. All right, so now let's go ahead and plot. All right, so let's plot the actual predicted value. The red is the predicted value for each of these. Now, the x-axis is the same, -3 to 2.7. -3 to 2.7, I've got the same x-axis values, but now I'm including the predicted value. What has happened is that the magnitude of the predicted value around -3 is so large off of this that it has completely squished the scatter plot. Every dot that was in that previous scatter plot is here, but now the scale is so screwed up that it looks like it's just a flat horizontal line, but we know that it's not. We know that it's like, overall it's got an oblique line trend. The magnitude of this, 1 times e to the 9, scientific notation of 9 in the exponent, is for my y-axis. This is ridiculous. This is stupid. I have been smacked in the face by overfitting. I have horribly, horribly, horribly overfit on this model. But this is the goal. This is what I'm trying to do to show you so that you are protected from doing this when you are building your own model. All right, so now let's zoom in on this. Let's zoom in so we can see what the data actually looks like. Let's look, okay, well, you know what, if I didn't have any actual values on that, real low spike. Let's go ahead and just see what it looks like. All right, so here, notice that what happened was that spike that went really, really low is right here. It's like, woo, it went super, super far down, comes back up. It might be doing some other things in the middle. We can't really tell off of this. Then it comes up, it goes flat, then it goes back down. We couldn't even see this dip on the scale. Like there's a dip in here, and that's completely off this graph that's not even big enough to be picked up because this is so insane what's going on over here. Furthermore, this completely missed that oblique trend. Look at this. This is a flat line. Like that, like I don't even know how I did that. I achieved it. I was like, wow, what the heck happened here? Because this looks like a flat line. It's not a flat line. Polynomials are never flat when they have a degree greater than 1 or greater than 0. So this is so nuanced with those tiny little predictor variable values with the coefficients are so small, it looks like it's flat. And it completely missed that oblique line trend. It should be going look like this, but it's not. This is a junk model. This is horrible. I feel bad about myself for building this model. As the polynomial degree increases, the model fits the training data more closely, which results in a decrease in the mean squared error on my training data. But at a certain point, I keep on making the training data MSE smaller, but then at a certain point, I start also making the the validation and test MSE increase. So at a certain point, I reach optimal degree, which we'll show in a moment. I reach the right degree that I want. Then training MSE keeps on decreasing, but test and validation MSE starts increasing. And so that's when I've hit that critical point that I've overshot what I want. Here I've grossly, horribly overshot what I actually wanted. All right, so here the model is picking up a lot of nuance and variations inside the training data that just isn't present in the overall population. All right, so now there's something else to talk about. Let's talk about the bias and variance trade-off. Total prediction error is a summation of three distinct errors: bias, variation, and irreducible error. Bias is that the model the model is giving me a modeled expected value of a value that is different from the expected value of the data. And so when from a theoretical statistics point of view, there is a conditional average for the target variable given the predictor variable values. And that's what I actually want to get in my prediction. Now, when I run my prediction, well, if that's off, if the predicted value does not equal the expected value, I have bias in there. Maybe it's too high, it's too low. It's going to vary for every single combination of predictor variable values. All right, so that's, bias is addressing the expected value difference between prediction and my target variable itself, conditionally. Now, the variance is the variability in what happens that, there's just things that, there's fluctuations that we observe in the training data that are deviations from the population, like expected value. And so the variance aspect means that, things just don't, get nailed down as well as we want them to. High variance suggests that the model may have some noise in the training data that could, lead to some problems. Now, the next one is irreducible error. The irreducible error are aspects of the situation that we just can't address with our predictor variables or the model structure. That irreducible error are things that just mathematically we can't account for with the tools that we are using. Maybe if I get some more predictor variables, maybe if I try a different mathematical structure, I might be able to pick it up, maybe not. Sometimes it's just not available. Especially when we're dealing with things like human performance, there's just factors that just aren't measurable that come into play. Like, is somebody having a bad day, having a good day? Aspects of like psychometrics and human performance that we just can't anticipate in what's going on. And so in the bias variance trade-off, models with high bias tend to have a low variance and tend to lead to underfitting. Low bias models tend to have high variance and lead to overfitting. That's when we're in the situation that this is a fixed total error and our irreducible error is like fixed. And so this is more of a theoretical construct where this gives us like a mathematical formulation that it's possible if I want to reduce my variance, I could actually compensate with a bias. All right, so now let's talk about finding the optimal degree. So let's go ahead and redo this polynomial fitting, but this time I want to go degree 1, degree 2, degree 3, degree 4, go all the way through all the possible degrees, and then check to see which one is the best. All right, so here's the code for how I did this. All right, and in this, I'm doing I'm using a series of for loops. And so in this, I am I'm doing polynomial features. So this is the object that does the transformation. Here I'm doing the transformation. Here I'm fitting and transforming on this for loop. Then I am taking the squared error of it, and then I'm using that to figure out what is going to be the optimal mean squared error that I can produce. Okay, and so here I'm going off of validation. I'm finding where do I have the minimum mean squared error for validation, and so we can see that was degree 2. Degree 2, I did degree 100. I went nuts. It went off the rails. And so we can see that here is my test MSE, which is about 3.2. Train is about 0.39, and then validation is 0.31. All right, so you'll notice that test and validation is actually lower than training. That's okay. That's an indication that I don't really have a problem with overfitting. Now, if I saw training was 0.1 and I saw test and validation were 0.3, that would be a sign of overfitting because that's a decent gap between them. All right, and so let's look at the plot of each of these. So the blue is the training. Okay, so we can see that it gets lower and then it just basically gets off the rails. This is definitely because there's definitely some numerical instability going in on this one. And then orange is validation, green is test, and we can see that we reach as low as we're going to get pretty early. Like it wasn't worth it to even bother, going above 20, maybe you could have gone out to like 35 or so, but beyond that, you can see that it's just junk. And look at what we have here for like around a little bit greater than 70. There's something bizarre happening, and that's probably because of numerical instability. But this just kind of reinforces that we want the simplest model possible that does the best job possible. So here I've got a range. Just looking at this graph, I could go from from 1 all the way up to, let's say, 38 or so, maybe 35, something like that, and get about the same statistics. Okay, well, what do I actually want? Well, I want the simplest model that gives me, practically speaking, the same performance. So I would be going towards the left-hand side here, where we see a dip. So like around, within 5 for sure. So 5 would probably be the most, the largest for the degree. Now, if I change my training test split, if I redo that randomly and rerun it, I'm going to get slightly different values for this. I might want to consider doing this a few times to make the final decision on this. But ultimately, I would have been better off with simple linear regression degree 1 than with degree 100 for sure. Even though degree 100 had more parameters, had more opportunity, but it didn't work out. All right. So what I want you to do for your homework, I want you to take your own data set that you find interesting, something you're excited about, and I want you to fit a multiple linear regression model where you grossly overfit this bad boy. All right, I want you to overfit. I want you to intentionally throw in as much stuff as you can, do feature engineering, throw in every kit and caboodle thing you can get, and I want you to experience overfitting with the goal of never doing it ever again. All right, and so then after you do that, and I want to use multiple linear regression. Multiple linear regression is by far the easiest to understand. It has the strongest theoretical framework. It's good for interpretation, hypothesis testing. I mean, it's super powerful. And it's a good place to start if you're learning machine learning. Then after you do that, after you fit the model, I want you to use the same predictor variables, but now I want you to run lasso regression. Lasso, what's going to do is it's going to add a penalty to the fitting aspect, and it's going to choose to push out predictor variables that are not useful. And we interpret what it does, it actually gives a coefficient of 0 for predictor variables that are not useful. And so when you get a coefficient of 0, we interpret that as it's not in the model. And so then I want you to do lasso, and I want you to compare how they perform. So grossly overfit your model using line of best fit, ordinary least squares, linear regression, then use exactly the same predictor variables with lasso. Lasso can do feature selection for us. Then just check to see how they did, compare. Lasso will do feature engineering for us, but sorry, it will do feature selection for us. Lasso will do feature selection for us, but it's not a good idea to rely on algorithms to do feature selection. We want to always have like adult supervision of our feature selection. Because what will end up happening is that you'll have two variables that are performing very similarly, but you know from subject matter knowledge that one is better than the other. Well, Lasso, because of fluctuations in the data, will pick the wrong one just because it doesn't know any better. It's an algorithm. It has no way of knowing the subject matter knowledge. So when we're doing our feature selection, we don't want to rely on the algorithm to do it. I'm having you do that here just because I just want you to go through the practice of it and something quick and easy to be able to compare two models. That's all I've got for you. Life is short. Do math.